The last presentation for today will be by Erin LeDell, Scalable Automatic Machine Learning. And Erin, thank you so much for being here today and taking your time with H2O.ai, which is quite a well-known company in the space. So we're very eager looking forward to what you have to share with us.
Okay, can you hear me all right? Hopefully, probably won't get a response, but yeah, thanks for having me. My name's Erin LeDell. I'm the Chief Machine Learning Scientist at a company called H2O AI, which is headquartered in California, but we are a very remote company having many offices, including several in Europe. So yeah, it's nice to be here. I'm going to talk today about generally about automatic machine learning and some of the attributes that I think are important in the H2O iteration of Auto ML is we try to be very scalable, and we're working a lot on efforts in the responsible AI space as well, which I will touch on as well. So that's sort of an addition to the talk. I think the original title was just Scalable Automatic Machine Learning. So this is the agenda. So this is kind of an overview of what I'm going to talk about. So we have what is Auto ML, just at a very high level if you're not familiar with the topic. And then I'll show you briefly what is H2O Auto ML. This is the tool that I lead the team for at H2O and was the original creator of. And then I'm going to talk about some other topics in sort of the responsible AI space. So what can we do to sort of automate some of these important concepts such as explainability or interpretability or fairness? And then I'm going to just briefly mention a new research effort that I've been working on, and which is now part of the H2O software, something called Admissible Auto ML or Admissible Machine Learning. So just for those who are not familiar with Auto ML, so one question we could ask is why are we trying to automate machine learning? So, I mean, there's a lot of obvious reasons, but some kind of an algorithmic reason is that there's not generally one algorithm that is the best for sort of all data sets. So just the general process of doing data science generally involves a lot of trial and error or testing out a lot of different algorithms. And this is because there's not just one single best algorithm. So ideally, it would be nice to kind of automate this process because it's sort of a laborious thing to try out a bunch of different machine learning algorithms and a bunch of different, let's say feature selection techniques or feature engineering techniques. But it just kind of comes from this concept of if there was, one best algorithm, we could just use that all the time, but that's not really the case. So a lot of AutoML approaches would be some kind of blend or experimentation across a number of different algorithms. And that's how we do it at H2O as well. So then what are more specifically some of the goals and features of AutoML? So I would say this is just sort of my opinion of the topic, but I would say one of the main goals is just to train the best model in the least amount of time. So that time could be effort in terms of like engineering time or like coding time, how long it takes you to actually write the code to train the model, and then also how long does it actually take you to train the model once you start training it. So the goal would be to sort of reduce on both ends there if we can, as much as possible, with sort of the goal of efficiency. And then another sort of goal or feature is it reduces the amount of human effort. If you have kind of a single function that can do all of this sort of data science experimentation, it's just frankly just a lot easier to write one line of code versus hundreds or thousands of lines of code. So another sort of feature of AutoML is that then if we make it this simple with like a simplified interface, the expertise required to do machine learning is reduced. So we can make this accessible to people that let's say don't have 10 years of experience or a PhD in machine learning. This could be, somebody relatively new and familiar with, the basic concepts of machine learning and how to validate models and kind of how to make sense of the results. So this very much broadens the number of people that can participate and the number of problems that we can solve. And then another just general goal, I think, is just to overall improve the performance. So we don't want to just get a model, we want to get the best model possible. And that's not guaranteed in any AutoML system. There's probably a human out there that could beat almost any AutoML system given enough time and expertise. But we just generally want to improve like the baseline for machine learning problems. And then another nice feature of AutoML is it can serve as a baseline in any kind of like scientific research or any application, or even just in a normal machine learning setting. Like you could just run an AutoML tool and get a good baseline to start, and then your goal could be to improve from there. And then you have a nice solid baseline that you can count on as like we know we can do at least this well. So I would probably kind of divide AutoML into a couple different processes. So there's sort of the data preparation or feature engineering, all of that type of data related stuff. Then there's the generating of the models. So at this point in time, most AutoML tools require really generating quite a large number of models to do the search. I think in the future, we will get to a point where we can sort of predict what the best model will be, and we can kind of skip this whole computational step. But at this point, this is generally how AutoML tools function, and how you're going to get the best performance is by in a smart way, using your resources and generating a lot of models, and having a good search strategy to make good use of that time. And then this sort of last one is optional, but this is something that I use quite a bit in my work, which is ensembling different models together. So you have maybe a lot of different types of algorithms and different types of models, and you can blend them together in what we call an ensemble to get better performance. And if you're new to AutoML, this is a blog post that I wrote. It's actually a few years old now. This is from 2018. We first released H2O Auto ML in 2017, so it's been out there for quite a while. We were one of the first sort of enterprise tools for AutoML. But if you're confused about, what is AutoML, what are the different tools, what are the different spaces, this article kind of goes into that at a high level. I would say you can pretty much divide the AutoML space into subsections by data type. So we have AutoML for image classification, for text, and for sort of standard tabular data like that you would find in a database. And so the techniques are very different in all those domains. So I would say first think about what your domain is, and then you can kind of figure out what the path is to finding the right tools to do that. Okay, so H2O Auto ML, I just want to give you an example of one AutoML tool. This is the one that I make myself. So just first of all, what is H2O? So H2O is an open source machine learning platform, and it's very much designed for enterprise use. So the company that I work at, H2O AI, this was our original product, and it's from the ground up designed in open source to be an enterprise grade product. So it wasn't an open source project before and then became a company. So from everything is built from scratch to be very, very efficient and high performance so that you can use it in production. And we have customers in all the sort of Fortune 500 companies in healthcare, banking, insurance, et cetera, all using this in production. It's written in Java, but we have APIs in R and Python, also in Scala, and also a web GUI. So, R and Python are generally the two main data science languages that people know. So we have this high performance tool, but you can, give it somebody who just knows R or just knows Python, or even somebody who doesn't know any language and can use a web GUI could train models. And so that's just a high level background. So H2O Auto ML is sort of the, let's say next generation of H2O that's sort of built inside of that. So the first phase, let's say, of H2O was building all these algorithms, these high performance algorithms, and all the utility and functionality around that. And then at a certain point, I wouldn't say we finished that, but there's always new algorithms going into H2O, but we took a different direction, which is let's take what we have and automate this. So we have a huge number of algorithms and tools, like we could just build something on top of this that is basically automating the data science process. And of course, you can still use all the individual functions. It's sort of a preference whether or not you want to use AutoML or just coding everything sort of from scratch. So basically, what it does is it'll do some basic data pre-processing. It will train a random grid of a bunch of different algorithms. For example, GBMs. Deep neural networks, GLMs. We also have XGBoost in there, which is a very popular type of GBM. And we do this in a way, it is a random grid, but we do it in a way that we think is efficient and trying to make best use of the time that we have. And this is kind of a simplified version of what the algorithm actually is, but this at a high level is kind of what we're doing. We tune all the models so that they don't overfit. And then at the end, so actually this in a recent version of H2O, we have updated this. We actually do by default many more stacked ensembles than 2, but generally at each phase, we train 2 stacked ensembles, which is a type of ensemble that takes all the models that we have. So that's one version. And then we also have a more lightweight version where it takes the best model from each algorithm family. So like the best GBM, best deep neural network, et cetera. That's meant to give you kind of 2 different options. The all models is generally going to be the best performing because it's got everything in there. But, when we are thinking about putting things into production, we don't want like a 200 or 300 model ensemble in production. Probably we want something a little bit more lightweight. So we also give you that option. And then we have something that we call a leaderboard where we can, compare and contrast all the different models that we have. This is just basically what it looks like in Python. So you essentially, load the library, start the H2O cluster, which is basically the name for a Java process that you're running either locally or on the cloud. You import your data, you tell H2O Auto ML how long you want it to run, either in terms of time or number of models, and then you tell it what the data is. Here's your training set, which column are you trying to predict, and then you just press go. And then you get an object back, and one of the things in the object that's interesting to look at is the leaderboard. And this is similarly what it looks like in R. So everything that we have in Python is also in R. So we have full interface in each language. This is what it would look like in the GUI. So if you don't want to use code or your, hands are tired or whatnot, you can just basically pull up this GUI and start clicking around, and you'll be able to train AutoML as well. And then this is a snapshot of what a leaderboard looks like. There are more columns that we can add to this that have to do with other things like training time and prediction speed, et cetera. But generally, the first thing you might want to look at is performance metrics, so model performance metrics. And these are the sort of standard or some of the standard performance metrics for a binary classification problem. And so we just see all the models ranked there by their performance. In this case, it's being sorted by the AUC column. So that's just a performance metric that's often used in binary classification. And of course, we see the stacked ensembles coming in at the top, which is what we typically expect. And you, of course, don't have to use the model that's at the top of the leaderboard. You could pick any of the models that were chosen. And that's why we actually have other columns that you can add to the leaderboard to kind of sort and look at models in a different way if you have different priorities. Okay, so then one thing that I want to talk about is so we have, Auto ML at this point in the year 2022 is not a new thing. So this is something that, it's been evolving for a long time. So, nothing that I'm sort of showing you is sort of novel, let's say. It's a, so what I do think is novel is doing automatic explainability and automatic fairness and interpretability. I think that is a nice new, let's say, application of automation. And so I'm going to talk a little bit about how can we automate some of these other concepts in machine learning. So just first of all, what is explainability in machine learning? So model explainability is taking typically a black box model, so something that's not interpretable, let's say a gradient boosting machine model, for example, or random forest, something that's kind of dense and usually performs well. So in machine learning, there's usually a trade-off between how well something performs and how complex it is, or how hard it is to understand if you're a human. So explainability is the idea that we could try to at least explain why or how the model is making its predictions. That's different from interpretability, and I will talk about that after this. But one of the things that we created, I think, last year in H2O was this automatic explainability function. So we can basically, pass either a single model or a group of models. For example, you can pass an Auto ML object, which would contain all the models that you've trained in your Auto ML run, and we can do sort of automatic explanations. And some examples of what an explanation would be. So we could look at variable importance. That's kind of the most basic traditional sort of explainability tool that people have used for a long time. When we have many models that we're looking at sort of holistically as a group, we can do model correlation heat maps. So we can look at sort of how the models are correlated to each other. And that can be useful in terms of choosing which model to promote production. For single models, we then have something called SHAP contributions. So this is another sort of explainability method that's pretty well known. We can do that for at the model level, but also at the row level. So if you want to say, why did this particular example get scored in this way? Like, why is the prediction very high here? And we can look at like which features contributed to that being like a high score, for example. Partial dependence plots, I'll just show you what that is rather than try to explain it here. I'll show you in a minute. Individual conditional expectation plots and residual analysis. So this is something that we can just basically with one function, I guess with two functions. One, we do Auto ML. We get, one line of code. We get a whole bunch of models. The second line of code is H2O.explain. We get a whole bunch of explanations automatically. The goal here is really to make it easy to do this important work of producing more explainable models or more interpretable or more fair models. Because, I won't go into a whole discourse about, some of the harms that machine learning models can do in practice. But if they aren't sort of carefully looked at and examined, there can be, negative consequences. Like you could end up having a model that is discriminating against a certain group of people, for example. And yeah, there's not enough time to go into that, but just be aware that it's very sort of unsafe to just train a model and throw it into production and not really think about what it's doing. So here's an example of if we have a whole bunch of models. So on the x-axis, we can see different model IDs. They have the model type in there. So there's some GBMs, XGBoost, et cetera. And then on the y-axis, we have the different features. So this is a data set that's trying to predict the sort of rating of wines. So like wine score, like I think it's from 0 to 10 or 0 to 9 or something like that. So this is, based on these different attributes of the wine that you could measure, could we predict how much people like it, basically? So it's kind of a fun problem. This is a SHAP summary plot, what it looks like. So you can see all the features on the left side. So at the top, we see something called alcohol. So that actually is the alcohol content in the wine. So on the next plot, this is a partial dependence plot. I think this is kind of a nice example. So here we're looking at one feature, so the alcohol content. So on the x-axis, we can see how much alcohol is in the wine. And then on the y-axis, we can see sort of the score, the mean score of like how good people think that wine is. And what's interesting about this is pretty much there's a correlation between, if there's more alcohol, people like it better. So you can see the trend going up and to the right. And then at the very end, there's kind of like a little cutoff. So, or a little, let's say stabilizing of the graph. So to a certain point, people like more alcohol, and then if you add more, it actually doesn't improve the score. And in some cases here, these are sort of all different models, interpretations of this relationship. And so there's one at the bottom there that's brown, which is one of the XGBoost models, which is actually suggesting that if you add too much alcohol to the wine, that actually like reduces the score beyond a certain point. So it's kind of interesting to see how the different models interpret the different inputs in the data. So this is kind of what we're talking about when we talk about model explainability. Okay, so just next would be interpretability and fairness. So this is becoming a huge discipline in machine learning, and we're getting to the point where we are starting to have really good tools around this. I think there's still a lot of work to be done in terms of tools that could just automatically debias models, but we certainly have a lot of good tools with respect to measurement. So these are two different things. So I'll explain quickly what is interpretable machine learning. So interpretable basically means that either techniques or models which can be understandable to humans. So we're dealing with complex data in high dimensions. So most of the time, unless we specifically choose an interpretable model, we're not going to have much interpretability in machine learning. So two inherently interpretable models would be linear models or decision trees. Those are kind of the main two that people talk about. There are others as well. And note that this is not the same as explainable ML. So just so you know, there is a difference between those two terms. So as I mentioned before, explainable ML, sort of the goal is to try to explain a black box model, a non-interpretable model. And with interpretable ML, the goal is to actually produce a model which is interpretable, or using other tools. It doesn't have to necessarily be that you're producing an interpretable model, but there are other techniques. For example, the partial dependence plot that I just showed you, that's an interpretability method, in my opinion. So you could also consider it an explainability method, actually. But yeah, there's just different techniques, and I'll talk about a new one that we created at H2O. And then a related topic is fairness. So these are, not the same thing, but often you need some level of interpretability or at least explainability to assess the fairness, or especially to mitigate the fairness if you want to figure out how to get rid of bias. And this is really, what is fairness? It's kind of a undefined. It's almost too broad to try to define. It kind of describes a broad set of problems. And one of the reasons why this is hard is because there's often like a push and pull between individual fairness and group fairness. So I'm not going to totally explain what the difference is there, but if you think about, like, if you want two people that are basically the same to get the same score, that's individual fairness. And if you're talking about group fairness, it's like a whole group of people, let's say, divided by gender or age or some other typically protected variable. That's called group fairness. And one of the other tricky parts about fairness in machine learning is that sometimes when you make a model more fair for one group, it actually makes it less fair for another group. So then there's this constant question of like, how do we balance all of this? And it's a very complicated thing. And so the other issue is that, when we talk about fairness, generally, we kind of move into the space of actual law and protected attributes. And of course, that's different in every country. And sometimes it's not so clear what it even means. So there's a lot of fuzziness all around. So this is just a more formal definition. So fairness in ML refers to techniques for measuring and or mitigating disparate impact on subsets of people defined by protected attributes. And this, this is one definition, let's say. And disparate impact just means that there's a difference in how, let's say, accurate the model is for certain groups. And that can have all sorts of wide-ranging repercussions down the line. So for example, in the US, we have certain laws. There's several US laws that protect consumers from credit discrimination. So the regulated industries are typically where you see people talking about machine learning fairness because it's actually required. So, for example, lending. So if you apply for a mortgage on a home or if you apply for a credit card, those are sort of protected by US law. So it's actually illegal to discriminate on the basis of these different attributes here. So race, color, religion, national origin, sex, including sexual orientation and gender identity, marital status, age, whether or not you're receiving public assistance from the government. So basically a lot of things. And it's very important because there's laws for a reason. Is because there was a lot of discrimination, especially in certain groups trying to get mortgages and being denied. So this is kind of like what inspired this new, let's say, domain of machine learning, which we're calling admissible machine learning. So this is one of the goals of admissible ML is to address the issue of fairness through unawareness. So one of the things that people sometimes do when they don't want to introduce bias into their model is they simply remove the age column, the gender column, the race column. And then they think, okay, I removed the data, so I'm good because there's no way that the model could be biased because it doesn't even have access to that data. And this is sort of a largely, sort of debunked claim. Like this is not true that you can just remove the variables. There's lots of things that could be leaking this bias into your model that are not specifically encoded as those protected features. So one of our goals here is to sort of find and identify and filter out these other features in the data set that you might not think they would leak this kind of information, but they do. And so the process is finding and filtering and just getting rid of sort of the dirty features from the get-go so that when we train our models, they're sort of much more fair or at least reducing some of the bias. And let's see, I have not very much time left, so I'm just going to quickly introduce just this new tool that we call the Infogram. So it's just a way, so this whole approach is, we have a paper that's published, but it's, so there's references at the end of the talk that you'll find, but basically this is a new tool. So if you think about like partial dependence plots as a tool for interpretability, this is just another tool for interpretability. It's based on information theory. And one of the things that we can do is we can basically calculate a score, which we call safety index, for sort of how safe is a feature. And the relevance index is basically how important is it to the predicting the outcome. So you could think about that as variable importance. So variable importance and safety. And then sort of everything up in the right-hand corner is considered, we can set these thresholds wherever we want, but generally, everything on the right upper hand corner of the infogram is what we call the admissible features. So those are the allowable features. And so the goal is to identify features that have, very low safety levels and not very much relevance as well. And so we kind of put these all together. We kind of introduce this concept called Admissible Auto ML. So the goal is to create an automated algorithmic risk assessment tool. So one of the reasons that people don't do fairness stuff in practice is that it's hard to do. There's lots of tools, like everything's sort of disjointed. You might have to know a lot about fairness to actually do it. So what we're trying to do here is to make this completely automated, so that we can, so there's no excuse not to do it, essentially. It's just a button, you press it, and you figure out how to assess the fairness of your model, and we can try to figure out if there's something we can do to reduce the bias. So that's the goal. And effectively what it boils down to is a feature selection method. So we're filtering out sort of the bad, leaky features. And I think I will end there. And I just have a few resources that I want to show you. So if you want to know more about the H2O Auto ML algorithm, we have a paper at that URL right there. And of course, in the Q&A that follows this, if you want me to go back to any of these slides so you can write down the URLs, let me know. Here's some more links. So remember, this is all open source. You can just try it out on your own data whenever you want. So we've got Admissible ML docs, we've got Auto ML docs and tutorials, and then the auto explainability thing as well. There's some general H2O resources and my contact information. So that's where I'll leave it, but we have, I guess, about 15 minutes to do Q&A. So I guess feel free to ask questions.
Well, Erin, thank you so much for your presentation. I think what was very interesting as the last takeaway for today and the last presentation for today is fairness in machine learning, but also in discrimination in models. I have a few questions from the audience if I would like to start off with. It was a very insightful presentation. Could you elaborate on a few techniques, ideas you could use to accomplish interpretability in Auto ML?
Sure. So I think, one of the things here, I'll go back to the interpretable section. So one of the things that I mentioned is, really when we talk about models, interpretable models, that would be, a linear model or a decision tree, or maybe a generalized additive model or GAM. So if you want to have interpretable models in an automated way, for example, you could use the H2O Auto ML function, and then there's, it's completely automated, but you can also customize it how you like. So if you want to turn on and off certain algorithm families, so let's say you just turn off all the complex models. So get rid of deep learning, GBMs, random forest, et cetera, and you can just leave the interpretable models. So that's one way to do sort of interpretable Auto ML. Because even with a linear model, you do have to train the model, and there you could do a grid search and whatnot and try to get the best linear model. So that's one way of thinking about it. Another way of thinking about it is to use interpretability methods on Auto ML. So that would be more closer to what I talked about at the end, which is using an interpretability method, for example, the Infogram. So this this method is actually a data method. It's not necessarily tied to AutoML. You can do whatever you want afterwards. You could train your own models. You could use AutoML, whatever. So the other tools that you have available in the interpretability space would probably be just more specific to looking at the data itself. So that could be, and I will say that this method does use machine learning to train and to estimate certain parameters inside of this process. So it's not sort of devoid from machine learning. There is machine learning that happens inside to produce this data. However, I would still consider it to be more of a data method. So then the last thing would be like something like the partial dependence plots. This is obviously trained on, like in this case, we have a whole bunch of different models here that we can look at. So yeah, interpretability and AutoML, they kind of go together, but you know, you know, you have to either start with interpretable models or use interpretable methods to look at and explore the data, and that might inform you on different choices you could make.
That's a very good,
so hopefully that answers the question.
Very good answer. Then I have another question from the audience, which I think is an interesting one also from my side. How about using Auto ML in an unsupervised and reinforcement learning?
Yeah, so there are different ways to automate unsupervised learning. So there's sort of very basic things, like if you think about like k-means clustering, there's ways to automatically choose the k, that kind of thing. That would be very like a simple version of that. Reinforcement learning is something that's used in the AutoML context with respect to deep learning. So somewhere in the talk, I mentioned a blog post that kind of reviews the different domains of AutoML. So one of the reasons that I wrote that post was it was around the time that Google came out with their AutoML. So they called it Google AutoML. And so everybody started asking us, what's that versus yours? Like, what's the difference? Why are they both called AutoML? And so one of the goals of that article was to kind of split people down to different paths. So if you have image data, for example, you're trying to do AutoML in the image space, you'll use a whole different set of tools. Maybe I didn't mention this, but H2O Auto ML is specific for tabular data. So this is the data that we see most commonly in the enterprise. So people just having, you know, tabular data in databases or whatnot. So if you're in a whole different domain, image, there's a whole bunch of different techniques, and a number of them do involve reinforcement learning. And generally, when you're in that space, what you're doing is something called neural architecture search. So you're trying to find the best deep learning model for your image classifier. And yeah, one of the popular techniques is reinforcement learning.
Okay, that sounds pretty good. I think that the audience is quite happy with your answer. Another question for you. Auto ML faces problems such as data and model application, for example, with high quality labeled data that is far from enough, and data inconsistencies during offline data analysis will cause bad effects. How do you address this at H2O?
I think the question is sort of generally asking about data quality. Like, is there a way to sort of, maybe, I don't know if I'm misinterpreting the question, but maybe is there a way to sort of automatically detect this type of issue? You know, I think that these types of tools, so any kind of like explainability tools, those are key, key tools that you can use to look for, you know, issues in your data. So, I mean, that's why I said earlier, like it's very unsafe to just train a model and throw it into production, because you might, you know, without really digging deep into the data, there might be things that you don't expect to be in there or that are in there by mistake. There's all sorts of weird stuff that can happen with data. So I think, you know, one answer to that would be use the resources that are available in terms of interpretability, explainability, et cetera, to kind of look at the models afterwards and try to make sense of it and try to see if, one thing that I see often is, let's say, you go back to the variable importance plot, and maybe a variable that you wouldn't expect to be way higher in importance than everything else kind of pops out, and you might think like that's odd, like what could be going on there. I mean, that's something that happens often, and that might be a symptom of what's called data leakage, where you accidentally kind of leak the outcome into the features. It might be some other, weird artifact of your data. So just, hopefully the variables that you have in your model actually are somewhat meaningful so you can make sense of them. When you get into the very complicated like feature engineering, where you start with some features and then they end up being like very uninterpretable down the line, like you combine a whole bunch of things, that's where it can get a little bit confusing, because you might see stuff and then not have any kind of explanation for why it's ranked high or whatnot. And then there's other things that you can do that are I don't know if it's an appropriate addition to my answer, but basically just sort of systems in place in production to monitor the models to make sure that things are looking how you would expect. So, for example, if you want to detect data distribution shift, there's certain methods to do that. That there's things that once the model is deployed and everything was fine when you deployed the model, then there's, of course, if you're generating new data and feeding that in or scoring new data, there's other things that you might want to look for. So there's all sorts of, I would call all of that stuff in kind of the ML ops space. So you can also measure robustness, et cetera. So hopefully that was
very clear. So we only have a little bit of time left. So the last question, do we have support of laws, regulations, and industry standards for Auto ML?
Do we have support for laws and regulations for Auto ML? Well, number one, that totally, I think, depends on where you live, what country you live. Europe is for sure ahead of the US on this. And they, there are laws that have been introduced that do, this would not be specific to Auto ML. This would be just any machine learning model. And I don't know of any laws or bills or anything that's been introduced that is specific to Auto ML. So, there's typically what I've seen happen is there's some, legislation introduced, and one of the difficult parts is they'll say, we need to have the models be interpretable, but then there's not really like a technical definition of what does that mean, how do we verify that, et cetera. So what would be great to see in that space is getting more sort of tool makers, algorithm people involved in working with legislators or politicians or whoever is interested, government officials in these things, and kind of connecting the dots. Because I think a lot of what I think might happen is laws will get passed, and then there's not really good guidance about how to implement that and how to verify if you're in compliance. And so we want to have laws actually have teeth, or that are meaningful, that we can adhere to.
Yes, absolutely. And by the way, we're finishing our time here. But thank you so much for your contribution today, Erin. And I really had to laugh a bit about the alcohol example in the presentation. That was fun. I think we need to see more of these kind of like live use cases that make artificial intelligence more, understandable, let's say, to the general population. And these kind of use cases really make a difference there. The same as that we see that in the fintech industry, right? And the banking world, the regulations are getting more tight. And we might see that on artificial intelligence as well. So. I would like to showcase this to you. This will be sent your way for your contribution to our presentation today. Thank you very much.
Thank you.
Yes, thank you very much for dialing in.
Appreciate it.
Yeah, and we thoroughly enjoyed your presentation.
Thank you very much.